particle is at 20 centimeters from the center. So PC is 20 centimeters, whereas the radius of the sphere itself is given to you 60 centimeters, and the refractive index of glass is 3/2. So now you have to see that for each of these observers, where does that particle appear to be? And for that, you have to use this formula, that mu2 by V minus mu1 by U is equal to mu2 minus mu1 by R with signs. And here the refraction in this formula, the convention is, it is from mu1 to mu2. So the rays are going from the medium which is having refractive index mu1 to the medium which is having refractive index mu2. Yes, so I think we have all the participants, including myself, safely into the meeting again. So let's work this out again. So we will of course use the formula to understand what the value of the position is. Okay, but we'll also eventually justify it with the ray diagram. So let's solve each part in one, in separately. So let's say I am solving this part first. I am solving for the observer E, okay, or the observer E, who is actually to the left. So for him, what is happening is that the interface is this one. The principal axis, let us say this. So this is the pole as far as A is concerned. This is the center of curvature, and this is the object, which also write as P or whatever, where we know that this distance is X. So that X is equal to 20 centimeters, and whereas the radius in terms of magnitude is 60 centimeters. Okay. So for the observer who's on this side and the object which is inside the glass, like this, 3/2, refractive index of air on this side is 1. So in terms of rays, what is happening? The rays emanating from this, say at a point like this. Now, what is the normal at this point? The normal would be this one. This would be the normal line. And as you know, the ray is going from glass to air. So it will tend to bend in which direction? It will tend to bend away from the normal. So instead of continuing like this, it will deviate away from the normal. It will go something like this, let's say. So this is a very exaggerated picture. Actually, you have to consider the rays which are very close to the principal axis here. But just for the sake of diagram, we've taken an exaggerated picture. So producing this back, you will get an image over here. So if we had gone by the derivational method, we take alpha, beta, gamma and all that, but we are not going to redo the derivation. Now to calculate the distance of the image, we will just use the formula along with Cartesian sign convention. So with the Cartesian sign convention, what we should do here is we should take this side as positive and we should take this side as negative. So for my observer E, now what should happen is we should take the object distance as positive of from his pole to that object. So the object distance is positive of 40. Whereas the radius of curvature with the proper sign should be taken as positive of pole to center of curvature. So that is plus 60. Okay. And the refraction, as you can see, is happening from glass to air. So in my formula, mu1 should be taken as the refractive index of glass, or 3/2. and mu2 should be taken as the refractive index of air or unity. So use this now and derive the value of V and see if that justifies our diagram or not. Okay. So along with this, now use that formula that mu2 by V minus mu1 by U is equal to mu2 minus mu1 by R. So all I have to do is substitute these things in. Okay, so what are we getting by substituting? Anybody got the answer? Yeah, got some replies. Let's see. Yeah, V you're getting as 45. Let me check. So mu2 the value कितना है 1 by V, which I'm finding out, minus mu1, which is 3 by 2, divided by U, which is plus of 40, is equal to mu2 minus mu1. So 1 minus 3 by 2 divided by R, which is plus of 60. So this should be my substitution. So 1 by V minus 3 by 80 हो जा रहा है ये, is equal to on the other side minus 1 by 120, minus half divided by 60. Let me see what this is giving. So this is further giving me 1 by V is equal to 3 by 80 minus 1 by 120. So that is 9 minus 2 by 240. So according to my calculation, the value of V, just check my solving, but it's coming out to be positive as expected, but it's 240 by 7. So approximately positive of something like this. Yes, 34.3, 34.2, something in that range, which you can see is justified. Okay. So you can also see that it is a virtual image. Okay. Behind the surface, behind the pole, which I have labeled as PA, at a distance of approximately 34.3 seconds. Okay. So this is how I am solving this with the proper sign convention and all that. And notice that in my sign convention, I have not flipped my sign plus minus just because the object is on that side. So I am now making the right side negative and all that. Not doing that. I am just following a Cartesian sign convention. That is according to Cartesian coordinate frame. That normally we take right of the origin as positive and left of the origin as negative. Okay, so ray diagram is getting justified with the value that I'm getting. Now just repeat this exercise for the other side, okay, where the observer is on the other side. This was the observer A on this side, and we did it for this guy here. Now the second observer is on this side, so the rays are coming like this. Again, they are going from glass to air, and again they are getting refracted by a concave surface, but the values will be different. Right. So anybody got the answer yet? Yes, I have some messages. Okay. So Manya, you're okay with that? Still, you got the first one. Now similarly apply the second one. Okay. So for the second case, you will have to readjust your position of the pole. The pole will become here. So just continue ahead. I'm just making the diagram and preparing the whole thing. Okay, so. Okay, so this is the pole as far as the observer B is concerned. He is viewing from here. So first, let's try to get an idea of what the ray diagram shows us. What kind of image to expect, real, virtual, behind the object, in front of the object, those things. Okay. So considering this as an incident ray on the object. Now, the normal at this point, as usual, is this. Try and get this correct. Oh. Now, once again, this ray will again bend away from the normal. But this time, bending away from the normal will give an interesting result. You'll see that the image actually goes behind. So the image will be further deep compared to where the object is. The depth of the image as perceived by this guy will be more, because it will tend to, instead of continuing straight like this, it will bend towards the normal, let's say. It goes something like this. Sorry, not towards, away from the normal. Angle of refraction is more. So when we produce this back, this should come somewhere here, let's say. So somewhere like this. Let's just say for argument's sake, it's this. Now remember, the ray diagram is only estimating, so it's not showing something very accurately. It's only estimating that the image, let's say, is somewhere over here for the object which is over here. So once again, the refraction is happening from glass to air. Okay. So glass to air, I should take mu2 as refractive index of air, or 1, and mu1 as refractive index of glass, or 3 by 10. Okay. Now we can consider this side of the pole as positive again, and this side of the pole as negative. Or, if you're more comfortable the other way, you can always swap it. You can take this side as positive and that side as negative. It will not matter. Ultimately, you will get some sign, and that sign will show you which side of the pole it is. Okay. So we will take u over here as minus of, according to my sign convention, PO. Okay. That is PBO. So that should here become minus 80 centimeters, isn't it? Because the radius was 60 and this is 20. So remember, this is 20 centimeters and the radius itself is 60. This side is negative. And we should take R as minus 60 centimeters. So let's substitute in the formula now. So just a second, I'll Restart the whiteboard. Just continue working on it. I'll just have to restart the OneNote thing. All right. So let's substitute in the formula again. So mu2 by v. So 1 by v minus mu1 by u. So 3 by 2 divided by minus 80 is equal to mu2 minus mu1. So 1 minus 3 by 2 divided by r, which is minus 60. So let's see what we get this time now. So 1 by v plus 3 by 160 is equal to plus 1 by 40. Oh sorry, 1 by 120 minus half. So okay, so 1 by v is 1 by 120 minus 3 by 160. So we can take 480 as our LCM. 9. So we are getting this as minus 5 by 480 as 1 by v. So v is coming out to be minus 96 centimeters. That totally makes sense because again this is telling you it's a virtual image behind the pole as seen by that observer at 96 centimeters depth. So this is the conclusion that we are getting by applying this formula to this diagram. So you can see both the refractions are happening at a concave surface from denser to rarer. But in one, the object was between the center of curvature and the pole, and in the other, the object was behind the center of curvature, in this case. So in one case, the image appears to be closer, whereas in this case, the image actually appears to be further. PI is a greater distance compared to PU. Alright, people. So hope both the parts of this question are clear. Yes, very good, Manishka. You got this correct. Okay. So in one case, the ray diagram was like this. So the object was between the pole and the center of curvature. So it appeared to be closer because the ray bent away from the normal like this. As in the other case, The object is actually beyond the center of curvature. For this pole is behind the center. So as it's bending away from the normal, it's actually appearing to be further behind. And you'll also see that if you were to use the real depth apparent depth formula from earlier, you'll get a very different answer because that would not correspond to this. Okay? In fact, one thing you can observe is that you can reduce the real depth apparent depth formula in this by taking r tending to infinity. If you consider a plane surface of refraction, then this plane surface is r tending to infinity. So that formula mu2 by v minus mu1 upon u is equal to mu2 minus mu1 by r. In this, if you make r tend to infinity, you will get that thing, that the apparent depth is the real depth divided by mu of 2 with respect to 1. This thing you will get it by using this. So you can think of the real depth apparent depth formula now as a special case of this, where the surface is not spherical, it is plane. So you're making its radius tend to infinity. Okay. So it's really the other way around that. Okay. Right. So now, apart from direct application of this, like a question like this, we see the next important thing is how we use this formula for finding the focal length of a lens. So now you can say we are coming to that part of the derivational part of the chapter, which is probably the most important part. Lens maker's formula. Or the formula used by opticians to actually fabricate a lens with given radius of curvature so that they get the required amount of focal length. So this is going to give us focal length of lens in terms of radii and refractive index. But this will be applicable for thin lenses. First of all, let us understand what is a thin lens. Okay. The formula that we'll develop will be only for thin lenses. For thick lenses, we will have to put a little more effort, like solve the two refractions individually instead of use focal length formula. So for thin lenses, the concept is that it is a refracting medium bounded by two spherical surfaces such that the thickness is absolutely negligible compared to their radii, the radii of curvature of the two spherical surfaces. So that's the definition of a thin lens. Okay, so for example, when we consider, for example, like a biconvex lens, it is a lens that is consisting of two spherical surfaces which are like this. Imagine one spherical surface like this and one more like this. They need not be same also. Okay? They can be of different magnitudes. So this is the lens that we're talking about. Okay, this is just a guideline. Okay, so the lens is actually a solid glass body, which is such that one surface of it is this spherical part of this sphere which I'm doing, and the other surface is this. So this object over here is what we would call a biconvex lens, because it is bounded by two convex surfaces. Okay. So if we label this surface as surface 1, then this surface as surface 2. Okay. You can see that this surface 1, that is this side, इसका सेंटर ऑफ कर्वेचर कहाँ पे है? ये वाले सरफेस का सेंटर ऑफ कर्वेचर यहाँ पे C1, और ये वाले सरफेस का सेंटर ऑफ कर्वेचर कहाँ पे? यहाँ पे C2. So they have individual radii, let's say R1 and R2. Okay. So two convex surfaces of radii R1 and R2 and center of curvature C1 and C2. But in between them, the lens is such that this thickness of the lens over here, this thickness from here to here, from pole of one side to pole of other side, this thickness, let's say W or whatever, width or thickness, this width is negligible compared to R1 or R2. So that's how geometrically the construction of a biconvex lens looks like. Okay. They don't have to be symmetric. They can be of same radius. If that happens, we call it a symmetric biconvex lens. They can be of different radii also. But the two bounding surfaces are convex and they are having some individual radii such that the thickness of the lens itself is negligible compared to the radii. Okay. So this is one example of a lens. Now other types of lenses which we'll be studying as part of this is something that looks like this, let's say, which is called a biconcave lens. So here if this is surface 1 and this is surface 2, now this time surface 1 is part of this. So the center of curvature of surface 1 is on this side. This surface is 2, so center of curvature of surface 2 is on this side. Okay. Similarly, we could have something like a plano-convex lens, or we could have something like a plano-concave lens, or we could have that very interesting type of lens which is called concavo-convex lens. So these are the various type of thin lenses we'll be studying. So this was biconvex, this is biconcave, this is plano-convex, this is plano-concave, and this is the interesting one which is convexo-concave. So these are the various type of lenses. Is how to determine the focal length of these lenses and then how to determine the UV formula for refraction through these lenses by making use of the thing that we've just derived. That formula mu2 by V minus mu1 by U. That formula. From that, how we can derive. So that is what lens maker's formula is all about. So we'll see that when light refracts through this kind of a thin lens, the light is undergoing two back-to-back refractions, and both of them are refractions of that type. Refraction at a spherical surface, then again refraction at a spherical surface. But one refraction will be air to glass, and then the other will be from glass to air. So by solving them back-to-back, we'll be able to determine the UV relationship, and from that the lens maker's formula. So let's understand now the derivation of the lens maker's formula. Okay. Now just for example, I am taking a biconvex lens, but the formula that will determine finally, or the formula that will develop finally, refractive index of glass is mu, and we have air on either side. So that is of refractive index mu. So the formula that will develop eventually with the Cartesian sign convention will be applicable in the same form, the same generic form for all the types of lenses. So this becomes a common pole. Generally, we would take two different poles for the two surfaces, but because the thickness is negligible, so this is a thin lens. Okay. Now let us say in this we are labeling this as surface 1. So its center of curvature is somewhere here, and we are labeling this as surface 2. So its center of curvature is somewhere here. And now let us consider a point object. Let's say it's somewhere here. This point object. Okay. So a ray of light incident from this point object, paraxial. Okay. I'm showing non-paraxial, but just imagine it's paraxial here. Now for this point, first surface ka center of curvature yahan pe, so the normal will be this line. So let's say it bends towards the normal because it's going into glass. So this ray now bends and it becomes like this. And it's now incident here where the second event is happening. For the second event, the incident ray is this one and the normal, let us say, is this line. So here it tends to bend away from the normal. So let's say after refraction, it again goes something like this, let's say. Oh, sorry, it bends away from the normal. So it will bend towards the normal at this point. It's something like this now. Normal is something like this, let's say. Okay. So it bends away from the normal. So let's say it bends away from the normal enough. In fact, let's assume it bends enough away from the normal to actually do this. And that's why it's finally giving me a real image somewhere over here. Okay, but see, if I solve each refraction one at a time, so let's solve them one at a time. So if I talk about the first refraction, it's happening from air to glass. So for that refraction, I don't need to worry about the whole lens. I just need to understand that the first surface of refraction was this one, this glass. Okay. Its center of curvature was here, C1. And my object was the object O. It was somewhere over here. Now for this, the ray diagram correspondingly, something like this. This incident ray after refraction will bend towards the normal and let's say go something like this. I'm not worried about the second refraction one. So I'm not drawing what's happening to that, but it will, let's say, go somewhere here. And it meets the axis at some point like this. Okay. So this is I1, this image after the first refraction. And for this, again, this was the normal. So as you can see, it has bent towards the normal. R is less than. Okay. So anyway, so for this refraction, the first one from air to glass. So air to glass, so mu1 I should take as refractive index of air. Mu2 I should take as refractive index of glass. Okay. And the radius I should take as R1, which in my diagram over here will be correctly substituted as, if this is the pole, with the sign convention, it should be substituted as plus PC1. It should be substituted as positive of this because I take this side as positive and this side as negative. Now the object for this is which one? It is O. So that means I should take U with proper sign convention as minus of PO, and the image is I1. So V I'm trying to find out how much that is. Okay, but V in the diagram will actually be equal to minus of PI. But I'm trying to find out how much that is. Okay. So let's substitute in the formula. So mu2, that is refractive index of glass, by V, which is V1, minus mu1, which is air, divided by the actual U, which will be substituted with proper sign when I'm doing it numerically. But here I'll just write it as U, is equal to mu2 minus mu1, so glass minus air, divided by the proper value of radius, which is R1. And again, R1 will be substituted with proper sign. So since it's a convex surface here, with proper sign, R1 would be a positive quantity. But had it been concave, then we would have substituted as a negative quantity. So this is my equation 1. And in this equation 1, you can see there are two unknowns. Okay. Or rather, there's one unknown, V1. So we can find out the value of V1 from this. Okay. Now let's come to the second refraction, because that's not all that's happening. My I1 is not the final image. So let's look at what the next equation is. So the second refraction, this is the one which is happening from glass to air at the second surface of the lens. So this is where we now have to understand the whole lens. So this is the second surface, but before that we also had the first surface like this. Okay. Now the incident ray on the second surface is this one. So it's actually the refracted ray from the first one. So where is it coming from? It is coming from that point, which was I2, sorry, I1, that point. It's not coming from the original object, right? Because the ray incident from the original object, that would be this one. But see, the ray that is incident on this surface is this. So for this, what is the object? The object is in fact I1. So what should I substitute U as for this refraction? I should substitute it as V1. I don't need to change sign or anything, because V1 only was from this pole, but we are taking a common pole over here. It was equal to, remember in my earlier diagram, it was minus of P, minus of P I1. So just by substituting it as V1, I've got everything correct. I've got the correct distance and I've got the correct sign also. Okay. So that is the object. And now after refraction, we saw that for the second surface, if this was somewhere the center of curvature, let's say. So this will bend away from the normal, and we had assumed it's bending away from the normal enough to actually converge. May not always happen that it will converge. It could still be divergent, in which case we'll get a virtual image. But so this is, and this is my final image. Okay. So the image for this refraction is I2, and because it is the final image, I can put the V as V2 as V only, because it's the final for the whole system. Okay, so this is the final for the whole system. Okay. Now I'll again go back to, provided my whiteboard supports me. Sorry about that, people. Just another software glitch. Just give me a few seconds here. Just give me a few seconds. I'll kill some other tasks on the computer so I have enough resources. Right. So for my second refraction, you can see the incident rays are these ones, the ones which are coming from refraction from the first surface. So they are appearing to come from I1. So that is why my object is actually I1 and my object distance is V1. Whereas my image is I2, which is the final image. So the image's position is nothing but the final image position. And it is happening from, remember, from glass to air. So it is glass to air. So I should substitute mu1 as diffractive index of glass and mu2 as diffractive index of air. So now let's incorporate all these things into our UV formula. So mu2, that is refractive index of air, divided by V, which is actually V2, which is the final image position, minus mu1, which is refractive index of glass, divided by U, which is V1, is equal to mu2 minus mu1, so air minus glass, divided by, one thing I forgot here, the surface that is refracting is the second surface. Okay. So R I should take as R2, which in this case with the proper sign would have been minus PC2, would have been the position of this center of curvature C2 with respect to this pole, but in general we are writing it as R2, so that's this. So this is becoming my formula. So this is the second formula. And in this I would substitute V1 from the first formula and get the value of V2, and that is the final image position. But in fact even that is not required. I'll show you why. Because if we just compare the two equations 1 and 2, just adding them will get rid of V1 and will give me the relationship of V2 with respect to U, and V2 is nothing but the final image position. So it will give you the relationship between the final image position and the initial object position U, which is what the lens maker's formula is all about really. Okay. So next, after understanding the derivation of this, how it has come from the particular refraction, next operation what we'll do is we'll add equation 1 plus 2 to get the lens maker's formula. Okay. So just take a look at this and just understand how the terms have come, the substitution in that formula, mu2 by V minus mu1 by U, that formula. Okay, so let's see what we get when we add the two equations. When you add the two equations on the left hand side, this term cancels out. You can see this term and this term here, they cancel out. And we are left with this term and this term. And on the right hand side, you can see that you can take the numerator common. So this is mu g minus mu a and this is mu a minus mu g. So you can take the numerator common, mu g minus mu a, and just write the equation now this way. Equation 1 plus 2 will give us this. Refractive index of glass upon V2 minus refractive index of air upon U will be equal to refractive index of glass minus refractive index of air into this term 1 by R1 minus 1 by R2. Now since I2 is the final image, okay, so we'll take V2 as V as position of final image due to the refraction by the lens. Okay, so having done that, this will become, oh sorry, this is mu a only, my mistake. Okay, just verify over there. It's not mu g, this is mu a. So we have mu a into 1 by V minus 1 by U is equal to refractive index of glass minus refractive index of air into 1 by R1 minus 1 by R2. Okay. In normal circumstances, mu a you will substitute as 1, so already you're getting the formula, but I'm just keeping it separate so that you understand what happens if I replace air with some other medium. Like if I take this whole lens under water, then everywhere there is air, you will replace it with water. So this will become mu w into this term is mu of glass minus mu of air into this, or you can just take this on this side and divide, and you will get this more convenient formula even, that 1 by V minus 1 by U is the refractive index of glass divided by air, so that is nothing glass with respect to air, nothing but that, minus 1 into 1 by R1 minus 1 by R2. But remember, everything is according to Cartesian sign convention. So whatever we substitute in the application of this formula, it has to be done with the Cartesian signs. So this is like the first version of the lens maker's formula. And now in this we'll put U as infinity. So we'll get the focal length as V, and that will become the proper version of focal length in terms of radii. So in this, remember, all quantities are with Cartesian sign. So this is the lens maker's formula in the first form. Okay, and then of course from this we'll derive the focal length. Okay. So next up we'll see that if we put u tending to infinity, that means incident rays are parallel to principal axis. Okay. Paraxial parallel rays. Then the value of v is equal to f. It is focal length by definition. This is the definition of focal position. Okay. So you substitute that in the above formula, put u tending to infinity. So substitute this here and you get this, that 1 upon f for the lens is now given by this formula. Refractive index of glass with respect to air, because we are doing the calculation of focal length for the lens in air. So this is the primary formula that we get. Okay. And the secondary formula that we get along with this is, if in the above equation, so this one is actually officially called the lens maker's formula, because it tells you what the lens maker has to understand, the relationship between focal length and the radii of each surface. Okay. And if you substitute back in the above equation, you get the second formula, that is a lens formula, that is 1 by v minus 1 by u is equal to 1 by f. So that is the UV formula for the lens. So this is what we call the lens formula. But when we say lens, remember we are talking about thin lens, or the UV formula for the lens. Okay, so this is you can say one of the criteria. After spherical mirrors, relative motion and all those things we saw there, this is the critical part now for refraction. Refraction by a thin lens. Okay, so let's quickly understand the application of both these formulae with an example. So let's take a case where we have biconvex lens. This side has radius, let us say 60 centimeters, and this side has radius, let us say 90 centimeters, and the refractive index of glass is 3 by 2 or 1.5. So we have to first of all find the focal length of the lens, and secondly you have to find the position of the image for this situation, that we keep an object over here, let us say at a distance of, let us say 120 centimeters from the lens, from the pole of the lens. Okay, so where will the image be located? So let's work this example out systematically. So first what we'll do is systematically we'll find the focal length for the given lens. So for that we'll have to understand that with sign convention, when we are properly using Cartesian sign convention, for light incident from this side, because our object is on this side, light, if it was coming parallelly from infinity from this side, okay, this would be our surface 1. And this would be the second surface it's sitting. So this would be our surface 2. So this surface, the first one you can see is part of this whole sphere over here like this. So its center of curvature is located where? Somewhere here, where we are given that this surface has a radius of 60 centimeters. So PC1 is 60 centimeters. There's the second surface, that's this surface here. So its center of curvature is here. So the distance PC2 is its radius, which is 90 centimeters. And the refractive index of glass is given as 3/2. So now for the focal length, first of all, we'll have to develop the Cartesian sign convention. So the Cartesian sign convention we'll take is that this side is positive, this side is negative. Not changing anything there. So we will have to take R1 as how much? Plus of 60. Because center of curvature of the first surface is on the positive side. Whereas we'll have to take R2 as minus 90. This is very important. If you don't get the sign correct, you will get the value totally wrong. Because this center of curvature C2 is on the left side. So we have to be mindful of that. Okay? And using this now, we'll calculate the focal length. 1 by F is refractive index of glass with respect to air minus 1 into 1 by R1 minus 1 by R2. So substitute everything correctly with the sign wherever applicable. So refractive index of glass with respect to air will remain 3/2 only. Because air we are taking as 1. And this will become 1 by R1. So R1 with sign is plus 60. And this will be minus 1 by R2. But R2 with sign is actually minus 90. So that's the critical step over here. Don't make the mistake of substituting this with wrong sign. So 1 upon F, as you can see, becomes half outside, 3/2 minus 1. 1 by 60 plus 1 by 90. Okay. Which you can write as 1 by 2 into, take 180 as the LCM, 3 plus 2. So that in fact becomes 360 divided by 5. I mean, this becomes 5 by 360. So focal length becomes positive of 360 by 5. Or the focal length becomes positive of 72. Now we have to interpret this correctly. What does the positive sign of the focal length means? It means that the focal position is on this side. This was in fact 60 centimeters, so it's somewhere here. This is the focal position. That's what we mean by getting focal length as positive of 72 centimeters. Which means that these rays, after they suffer deviation because of the two refractions, they will emerge out from somewhere here such that this is where they reach. If we take the rays parallel to the principal axis, this is what will happen. So it's showing you that this is rays coming from infinity will give you a real image at the positive value of focal length. These rays, this will give you a real focus point. Okay. And this is therefore what we call a converging lens. And that's why by nature the lens is becoming a converging lens over here. Okay, so hope this is clear, people. Just make a note of this. Okay, so I'm just minimizing this. Understand how we have got this. Alright, so this thing now it tells us that it is a converging lens. Because rays which are parallel to the principal axis get converged of focal length 72 centimeters. This is the meaning of this statement. Okay. And now very quickly let's work out the second thing, that when we keep the object in front of it at, we have taken the distance is 120 centimeters or whatever. And where is the image located? Yeah, 120 centimeters. So now once I know the focal length, it's just about applying the UV formula correctly. Okay. So I know that if the object is on this side, the rays are coming like this. So the focal point has to be a real focal point. So it has to be on the other side. So taking this as our pole, this as positive, this as negative. We'll have to substitute U as minus PO, or minus 120 centimeters. Whereas the focal length will be positive of PF, because it's on the real side. So that's plus 72 centimeters. And we'll use the formula 1 by V minus 1 by U is equal to 1 by F to find the position of the image. And that will tell us what type of image it is also. So substituting this now, 1 by V minus of 1 by minus 120 is equal to 1 by plus 72. Okay. So as you can see, you'll definitely get a positive V over here, because 1 by V will come out to be 1 by 72 minus of 1 by 120. I can take 12 common, but I could have taken 24 common. So 1 by 24 into 1 by 3 minus 1 by 5. So V becomes plus 180. 15 into 12. Okay. So plus 180 means back in the diagram, these rays will emerge converging in such a way that they will give you a final image, which is a real image at a distance of 180 centimeters. Okay, so that is the completion of this problem. So next time, that's where we'll conclude today. Now, next time we will look at more applications of lens maker's formula, and we'll understand in detail why concave lenses in general are diverging in nature. And for this kind of diagram, they will always give us a negative focal length. For light coming from the negative side, the image will be a virtual image on the same side, so it will be negative. Okay. And we'll understand the application of few more tricks and things while applying these, and combination of lenses, etc. But with this, you actually have enough ammunition to complete any problem related to lenses and any problem related to combination of lenses with mirrors, etc. So you can proceed with now trying to complete H.C. Verma's chapter, because the next part, which is optical instruments and all that, comes in a different chapter in H.C. Verma. So the geometrical optics chapter or the ray optics chapter is all about application of the concepts we learned to date here, and you can go ahead and try and solve most of the questions. So that's it for today, and please continue working on both mirrors and lenses, and of course the refraction at plane surface, spherical surface kind of problems this week. Because next weekend your test will be based on all the things up to this point, up to lens maker's formula and the lens formula. So up to these two formulae we have discussed in there, that is where your syllabus for the next test is. Okay. So that's it for today, and please keep sending me your doubts during the week as you are solving questions. I will help you out with that. Okay. And as usual, stay safe and make sure that you're maintaining all the frustrating but very necessary protocol of the lockdown and all that. All right. That's it, guys. Take care. That's it from me. All the best.